Hi, this is a complete schematic diagram of this altitude rate computer. The sensor is on the left here. It is supplied with a DC voltage of 12 or 15 volts. The output of the sensor is fed to a first amplifier. Actually, it is an attenuator because we have a gain of 0.2 with 100K here and 20K on the feedback resistor. So at the output of this first amplifier, we have a voltage which is proportional to the static pressure. And then we find the differentiator. So this is a big capacitor. It is this one here, 20 microfarads. At the output of this amplifier, we have a signal which is proportional to the rate of change of the static pressure. So this is the derivative of the static pressure versus time. Generally, in several altitude rate of change I have studied, there was a correction of the linearity before the differentiator. That is to say that this point of the capacitor corresponds generally to the altitude and not to the static pressure. In that particular case, we need to have a correction of this signal because the derivative of the static pressure is different than the derivative of the altitude. For a given variation of altitude, the variation of the static pressure is smaller at high altitude than at low altitudes. So this is why, in order to recover the rate of change of altitude, this value should be corrected. So one possibility is to divide this value by the static pressure. It is what it is done actually on that circuit. So the rate of change of the static pressure here is fed to this DAC. Actually, this DAC is configured as a divider. The output current here is the ratio between the input voltage on this pin, this is the resistor feedback pin actually, divided by the binary code. This is the 10 bits DAC. So it is the ratio between the voltage divided by this binary code. Okay, so the output is the current. So this current is translated into a voltage using these two resistors feedback, and then we have the altitude rate of change at this point, which is available on the rear terminal. The static pressure actually is available at the output of this DAC here. I will make a zoom. This altitude is modified using this ROM. Then this data is fed to the DAC in order to perform the ratio between the rate of change of the static pressure divided by the static pressure modified by the lookup table which is inside this ROM. The rest of the circuit is an ADC which provides the 8-bit data of the static pressure on these lines here. I will explain you now how this ADC works. So first, the voltage which represents the static pressure is available here on that line. So you can see that that line is connected to this resistor. So there is a current flowing into this resistor, which is proportional to the static pressure. So this is a summing node. The current which flows into this feedback resistor is the sum of three currents. The first current is the current we want to measure. The second current is an offset. This trimmer permits to adjust probably the zero. And there is another current, which is a sink current, which is the output of the DAC. The goal is to have a null voltage at this output. This is an error amplifier. If we suppose that we have 0 volt at this output, that means that the current which flows into this resistor is identical to the current which is provided by the DAC. In that case, the 8 bits, which are the input of the DAC, are proportional to the static pressure, because the current is the same here. The rest of the ADC is performed on the second board, which is on the bottom of this page. The error voltage here is fed to two comparators, which are here. One comparator is used to sense the error voltage when it is positive, and the second one when it is negative. There is a first threshold. The voltage is approximately 20-25 millivolts or something like that. We find these two counters which are cascaded in order to form an 8-bit counter. Actually, we have two clock inputs. One permits to increment the counting, the second one to decrement. there is a clock at 400 Hz. This clock comes from the transformer here. So the voltage is fed to this transistor, which permits to have a square wave here. So the square wave is fed to this gate in order to have a clean waveform at this output. The clock is connected to one input of these two NAND gates, and the countdown or the count up are enabled by the output of these two comparators. So when the error voltage is positive and above this threshold, then the countdown is enabled. There will be a change of the output of the counters, and this will modify the value of the output current of the DAC. And if the voltage is below the negative threshold, then the count up is enabled, and then there will be a change of the output data here in the other direction. So the goal is to have a signal which is in between here. So when the signal is between these two thresholds, we'll have a negative voltage on both outputs here. And this permits to have a voltage of minus 0.7 volt here and here. And this permits to have 0 volt on the second input of each NAND gate. And in this case, the counting stops and the value is stable here. And this value is proportional to the static pressure. It's a nice solution anyway. I think it was interesting to see this discrete ADC. On the right of this page, there is a detection of the validity of this system. So first, this error signal, which is here, is also fed to these two comparators. So when the signal is in between, that means that the ADC works. If it is not the case, one of these comparators will be at low level, and this will deactivate the flag. So there is actually an LED, which is the LED which is in the front panel. It is this one here. So this LED is active when everything is okay. That is to say that there is a high level on this point here. So this permits, after filtering, to turn on this MOSFET. And this MOSFET permits to have a current which flows from this point to the ground. So this permits the saturation of this transistor, which permits to turn on this LED and also to turn on this PNP transistor in order to indicate that the system is okay. And the second comparator senses the output voltage here, which is the rate of change. So if the rate of change is too low or too high, there will be also an error. The last thing is the power supply. There is nothing to say, so we have one transformer with two secondaries. One is used for the digital circuits, this regulator. It is this one, but I cannot see the reference. The second one is used for the analog circuits. So it delivers a positive and a negative voltage. It is this part here. So I forgot to speak about the reset. So during startup, this comparator generates a positive signal during a given time. It depends on the time constant here and the threshold, these two resistors. So this permits to turn on this MOSFET, and this permits to have 0 volt at this point at startup. This avoids a transient on this output. So at startup we have a known condition. There is something strange on this board. This is this diode here. So I have represented the diode as it should be. So this diode permits to avoid a negative voltage on the base of the transistor. On that particular device, this diode was mounted on the reverse direction. You can see this diode. It is this one here. And you can see maybe, I don't see if we can see clearly on the camera, but the diode is not soldered correctly. Okay, but you can see the seed screen. The cathode is on the left and the diode is soldered with the cathode on the right. That means that the junction is in parallel to the base emitter junction. There are two problems. The first one is that this diode doesn't prevent a negative voltage. And the second one is that when there is a positive current here, the current will be split in two different currents. So one current will flow into the base of the transistor as it should be, and there is another current which will flow into this diode. In this case, this diode is forward biased. So depending on the voltage drop for a given current of these two junctions, there should be a large difference between these two currents. So it is strange to find this kind of error on avionics, because normally after soldering we should verify at least the orientation of the ICs, the orientation of the diodes, and the polarity of the capacitors and so on. Obviously on this particular board this test was not performed. So this was the reverse engineering of this board. It took me about 1 day to complete this schematic. So that's all for the second part. On the next and last episode, I will perform some tests on this instrument. So that's all for today. Thanks for watching and see you next time. Bye bye.